Good morning everyone. I'm going to try to answer this question, can we fix noisy quantum computers? So let's take a minute and try to imagine what a quantum computer actually looks like. If at all you got an image, if at all you think it looks something like this, then you are definitely wrong, because quantum computers, if you search in Google, Google gives an image something like this. So what does this represent? Let's try to break it down, okay? So what do we already know? We know something called as classical computers. The desktops or the laptops that we use nowadays are all classical, and they use something called as bits, which is either 0 or 1, and then they are composed of logic gates, let's say AND gate, OR gate or NOT gate. What does quantum computer consist of, right? They have something called as qubits, and they are made up of quantum gates. For example, C0 gate, X gate, Y gate, we have so many quantum gates. So coming to bits versus qubits, if you see this picture, let's say that if this circle is in orange color, then it's 0, and if it's blue in color, it's 1. So bits is either this color or it's an orange or blue, but then qubits, they are some percentage of orange and some percentage of blue. So this particular qubit has almost 50% orange and 50% blue. So if I try to measure this qubit, what happens is there is a 50% chance that I end up with a 0 measurement, and there is a 50% chance that I end up with a 1 measurement. So how do we represent this qubits? Is using something called as ket notation. Ket psi is actually alpha times 0 and beta times 1. So this alpha and beta are complex numbers, and the modulus alpha square and beta square actually denote the probabilities with which we get either a 0 measurement or 1 measurement when we measure this qubits. So by normalization in probability, this normalization factor should add up to 1. So this qubits are generally in a superposition state of the number of possible states they can represent. So this is 1 qubit can be either 0 or 1. So if you have more number of qubits, it will be like 0, 0, 0, 1 and so on. So why do we even need quantum computers, right? What is the use? We can have classical, we were so happy with all the classical computers we had. So let's motivate this by a story. So Rapunzel and her friend the chameleon are so bored, and they wanted to play a game. So what Rapunzel was doing is she gives a number and then asks the chameleon to divide that number into its prime factors. So if I give a number 15, you know 15 composed of 5 and 3. These are the prime factors of the number. So this is easy, we can compute by ourselves. So what happens if I have a huge number? Something like this. It's very hard to compute. What happens if I give this to a computer? Let's say both a quantum computer. This is definitely not how a quantum computer looks like, but just for the representation purpose I am using this icon. And if I compare how these both computers perform this prime factorization, I get a curve like this, I get a graph like this. As the number of digits in the number that I have to factorize is large, as in like if I try to factorize large numbers, what happens is the number of operations that I have to perform when performed on a classical computer is something like this. Notice that the scale is exponential, I mean log scale. So this graph is exponential power constant times d power 1 by 3. And when performed in a quantum computer using some algorithm called a Shor's algorithm, it's a very theoretical algorithm, and that takes a polynomial time. So if you can see from this graph, shown that quantum computers achieves the exponential speed up, and people who are working in algorithms know that this prime factorization is actually an NP problem in classical computer. So quantum seems like it can solve it in polynomial time, which is a huge thing. So why is it exponentially fast? Like, let's say I have an input, this is some process in a classical computer. I give an input x and I have to perform this f of x. So what happens, how do I characterize the outputs for f of x? Let's say this x is in 2, n is 2. So what are the possible inputs I have? 0, 0, 0, 1, 1, 0 and 1, 1. So I have to perform this experiment 4 times to characterize what my function f is. So, in general, I have to perform this 2 per n number of times for an n dimensional input, right. But then what happens in quantum, if I have an input that is quantum, for n is equal to 2, guess how many number of times I need to perform this? It's just 1, because I can perform, I can get a state that has a superposition of all the inputs that I need, and then I just pass it through this function. What I get? I get all the functions output as I needed. So, then in general, for any n qubit inputs, I just need to perform it once. This is an exponential speed up, right. But what is the catch here? So, if you see this output, I said this numbers in front denote with what probabilities we get that output, right. So, all the numbers are same. So, if I try to measure this, I get any one f as an output, and it can be as random as possible because it all has equal probabilities. So, this kind of quantum computers cannot be used in all kind of problems. Let us say if I want to use a quantum computer to add 2 numbers or multiply 2 numbers, do you think it is efficient? No. Quantum computers can be used to solve only a few variety of problems. So, quantum computers are exponentially faster, does not apply to all problems and only for certain type of problems. And why is that certain type of problems very interesting? So, what kind of problems it involves is, I have to make sure that my f of the 0, 0 or 0, 1 etc. are zeros for all the f's except for one particular f. Let us say f of 1, 1 is alone 1, and then the rest of the f's are 0, then for such kind of functions, if at all I use a quantum computer, then I get the output easily, right. So, only for certain kind of problems we can use this. So, there is one problem called as RSA encryption algorithm. So, in this algorithm, this is the algorithm that we use in all the digital transactions that happen, all the credit card, debit card transactions we do. So, this encryption algorithm is based on the same game that Rapunzel and the chameleon played. So, if she gives a prime number, she just gives a number, let us say the encrypted number in the credit card, and if at all this chameleon breaks that number into prime factors, then this card details is stolen. Okay. So, if at all this chameleon uses a classical computer, it cannot be done, whereas if it uses a quantum computer, it can be done. So, what's still stopping us from breaking the RSA, right? If at all it's done, by now we cannot use all the digital transactions that we have. By now it should be done, right? So, there is noise. Quantum computers are noisy, and this happens because when we try to implement a quantum computer, all the even in classical computer, the circuit components are not very perfect, but quantum is very prone to noise, and it's very easy to mess up the probabilities that we have. It's very delicate, and this also happens due to the interaction with the environment. So, let us say I have this white color qubit, I am giving it to some quantum computer, let us say this does some prime factorization, and then I need an output of this gray color. This is my ideal output. So, if there is no noise, I get accurate results, and if that quantum circuit is noisy with some probability p, then if at all I give this white color qubit, just dies, and you do not get what output you intended to get. So, in the presence of noise, the qubit dies. So, how does this noise look like? How do we model this? So, if you see this is very similar to a classical erasure channel. So, 0 with some probability 1 minus epsilon remains 0, and 1 with some probability same probability 1 minus epsilon remains 1. With probability epsilon, this 0 and 1 both changes into an intermediate state of erasure state. Similarly, quantum, we have something called as quantum erasure noise, where with 1 minus p probability it remains in the same state, and with probability p it changes into an erasure state. And there is one more thing called as depolarizing noise, which with same probability it remains in the same state, and with probability p this I by 2 is a maximally mixed state, as in if I give an input 0, it changes into exactly half times 0 and half times 1, like it is maximally mixed, the superposition state I showed in the first slide. So, this is how we model noise. And in that presence of noise, how do we perform computation? Generally, we send, instead of sending this one white qubit, we send extra qubits for the purpose of error correction, or you can also think about it like you are performing the same computation again and again with the hope that you can somehow maximize the probability of the correct answer that you need. So, instead of sending this white, I am sending 2 friends along with it, and I get this gray qubit that I needed as the answer. So, I introduced 2 terms here. One is called redundancy, which is k. So, instead of performing the experiment once, I try to perform it thrice. So, the ratio is actually 3, and the number of ancillas, or the number of extra qubits that I send, is this blue and green that I have. So, it's the extra qubits is 2. So, why is this hard? If at all I can send extra qubits, or perform it again and again, and I can overcome noise, why this seems very hard? Because let us say that we are in a football field or cricket field, and I am searching for a needle in that. Okay. So, what I can say is, I can give you an area in which there is, no matter how hard you try to find or how many people you involve in finding that particular needle, you cannot find anything, you cannot find that needle in that area. So, similar to that, if you think of that example, so this error probability shows the error probability present inherently in the quantum computer that you try to implement. So, that error probability is somewhere between 0 and 1. So, if at all that error probability is above this red color line, no matter how many qubit friends that you send, or no matter how much you increase the redundancy, you cannot perform any computation. That is similar to saying that no matter how many people you involve in finding that needle in that cricket field, you cannot find it. But then if at all it is less than this green line, let us say, then I can say that in that area, if at all you have some optimal number of people, let us say that I have 100 people, then there is a possibility that I can find that needle. So, that region is called as the achievability region, and the region in which you cannot find is called as the Converse region. And then is it that simple? If at all I avoid the Converse region, if at all I avoid the area in which I cannot find, or in which I cannot perform a good computation, is it done? No, because let us see this graph, in which you see this is actually the era that we are currently in. This is called as noisy intermediate scale quantum, wherein the computers that we have, the quantum computers that we have, according to technology, has a physical error rate in this order, and the number of qubits, or the number of input bits the technology supports is very less, like in terms of some hundreds to thousands. So, as I told, even if I am in that area in the cricket field where I can find the needle, I cannot keep sending on more people. Let us say I have this area where I can find the needle, I cannot send around 1000 people, 2000 people to find it, because I have a very less number of people available as well. And also the thing is, the number of physical qubits that are available are also prone to noise. Similar to the example, you could take it as the number of people that I have available to search the needle can faint it at any time, right? They are not very efficient. So, when trying to implement a quantum computer, then what are the things that I should keep in mind? I should keep in mind the redundancy that is needed and the inherent noise present in the circuit of the computer are the very 2 important factors to achieving a good quantum computer. So, if at all I try to implement a quantum computer, let us say, what are the questions that I will ask? As I already mentioned, we need to understand what is the inherent noise that is tolerable by the quantum computer. That is, we have to avoid the Converse region, just say that I cannot find it there. And then what is the minimum redundancy required, or what is the minimum number of people required to search the needle, right? So, to answer this first question, we have to characterize the Converse region, the red color region that I showed. And to answer this question, what the minimum redundancy required, we cannot make them the number of people available to infinity, because we do not have that many number of people according to the current technology. We do not have that many number of qubits, right? Because we are in the NISK era. As I already told, the qubits are noisy and the number of availability of the qubits are limited to few hundreds. So, mathematically putting that model, let us say I have n qubits and rho of n is the representation of that n qubits, and then q0 of n is the quantum computation that I am trying to perform. Using some technology that supports this gate size of small g. Let us assume my computation is somewhat in layers. So, O1, O2, O3 till OL are the number of layers, and there is some layer D at the end, and this is the computation I would like to perform. So, as I said, the computation has some noise. So, every layer has some noise associated with it. So, this red boxes are the perfect noiseless computation done in that particular layer, followed by there is some noise that affects that each circuit. So, if at all I use this model and try to find what is the region that I have to avoid as well as what is the redundancy that I require. So, are we the first to do this? No. There are very limited literature, but then there are results. So, thanks to these authors, I would like to put your attention only to this part till this last result that came in 2022. The redundancy or the minimum redundancy k or the number of people that I need or the number of qubits that I need was not characterized. Okay, this was the recent result that came, and they characterized it as 1 by q of n, where q is the quantum capacity of the noise channel. So, I showed a slide how you model quantum noise as some channel. So, this q of n is actually the quantum capacity of that noise channel, and the probabilities are something like this. So, notice from the previous slide, G is actually the gate size. So, what happened is in all these three literature, these results are for some noise model called as depolarizing noise model, and this literature was for a general noise model N. But the problem with this literature was their bound actually kicks in asymptotically. That is, only when you have so many number of qubits or you have that efficient people or like large number of people to search the needle, then you can apply this bound. So, what the problem is, we do not have the technology. So, we have very less number of qubits. So, we need to make this bound non-asymptotic, that is for a limited qubit size. So, that is what we tried to do. So, we came up with a model to do that, and what is the redundancy that we got is our equation like this. So, in this equation, we try to capture the gate size here, and this ICN tensor G is actually the coherent information of the channel. As I told in the previous result, it was something related to quantum capacity, and this is coherent information. For people who have done information theory, this coherent information is very similar to something called as mutual information in classical terms. So, this is mostly like a quantum analog of it, and this is the result we got. So, if we see, we do not have any bound on n. We do not say that this bound only holds when you have large number of n or k. So, this is NISK friendly. You can apply it to the current technology that you have. And we have also captured the dependencies of the circuit, like you have this G here, which if at all you implement a circuit with different gate sizes, you can capture which circuit performs better or which circuit is more efficient. And this is also for generic noise models. It is like for any noise model n, you can apply it, not just for depolarizing noise. And then what is the converse region? If you look in this, if this IC n of G becomes 0, this computation fails. And also if you put in this equation, you can see that k is greater than or equal to infinity, right. So, if this term becomes 0, and for the values of noise p for which this term becomes 0 is actually the converse region that you have to avoid when building a quantum computer. So, these are the two results that we came up with, and what does these results imply? So, I have told you what danger zone that you need to stay off if at all you want a good quantum computer, and what is the resource k that you needed to compute. And so, to answer the question, can we fix noisy quantum computers? We can, provided that we stay out of the converse region and we use at least this many minimum redundancy for error correction. So, there is still hope. Thank you.